There is a kind of star that has a name before it has a body. Astronomers can describe its mass. They can describe its temperature. They can tell you how it forms, why it should be dark, why it should be dense, why it should drift through space like a frozen fossil of a sun. And yet, if you search the entire observable universe tonight, every galaxy, every cluster, every old halo of ancient stars, you would not find a single one. Not one. The object is called a black dwarf. It is not fiction. It is not a mistake in the mathematics. It is something stranger. It is a future object that the laws of physics seem to promise, but the universe has not had enough time to make. That is the controversy at the heart of this story. The easy version says a black dwarf is simply a white dwarf that has cooled down. That sentence is true, but it hides the real problem. A black dwarf is a scientific object without an example. It is defined by processes we understand, but separated from observation by time so enormous that the current universe looks almost newborn. We are used to thinking that astronomy is a science of seeing. We see a planet, a nebula, a galaxy, a dead star, and then we try to explain it. But black dwarfs reverse the order. We have the explanation first. The object comes later, much later, perhaps so late that no observer like us will ever be there to confirm it. The familiar belief is that a dead star is finished. It burns out, collapses, cools, and becomes part of the background. But a white dwarf refuses to be finished quickly. It can spend longer fading than its parent star spent shining. And the pressure point is this. The universe is already 13.8 billion years old enough for stars to have formed, died, and seeded galaxies with heavy elements, but still far too young for even one ordinary white dwarf to cool into a true black dwarf. The death of a star is not the end of its story. It is the beginning of the longest fade in the cosmos. To understand why this matters, we have to start with the object that black dwarfs come from. A white dwarf is the leftover core of a low or medium mass star, the kind of star that does not end in a violent core collapse supernova. Our sun belongs to this quieter category. It is not massive enough to build an iron core. It will not leave behind a neutron star. It will not become a stellar mass black hole. Its ending will be slower, more ordinary, and in a way more unsettling. Because ordinary endings dominate the universe. For most of its life, a star like the sun survives by balance. Gravity pulls every layer inward. Fusion in the core pushes outward by releasing energy. Hydrogen nuclei combine into helium under extreme temperature and pressure, and the energy released by that fusion supports the star against collapse. The star is not still. It is a controlled argument between gravity and heat, between contraction and pressure, between the desire of mass to fall inward and the power of nuclear reactions to hold that fall back. For billions of years, the argument remains stable enough that a planet can orbit nearby and call the light day. But the balance is temporary. Hydrogen in the core is not infinite. When a sun-like star uses up the hydrogen in its central region, the core begins to contract. That contraction heats it. Hydrogen in a shell around the core can begin fusing, and the outer layers respond by expanding outward. The star becomes a red giant. Its surface cools as it swells, but its total size and luminosity change dramatically. The star that once seemed stable reveals that stability was only a phase. Later, helium in the core can fuse into carbon and oxygen, but for a star like the Sun, that is nearly the last useful chapter of nuclear burning. Carbon fusion requires conditions that Sun-like stars cannot reach. The core becomes a dense mixture dominated by carbon and oxygen, but it cannot ignite the next stage. There is no long ladder of fusion leading to iron. There is no catastrophic iron core collapse. Instead, the star sheds its outer layers into space, forming a glowing planetary nebula, while the exposed core remains behind. That exposed core is the white dwarf. It is small enough to compare to Earth in radius, but massive enough to compare to a star. It is one of the strangest compromises nature allows. An object with stellar mass packed into planetary size. A teaspoon of its material would weigh tons. Its gravity is ferocious. Its density is so far beyond ordinary matter that everyday intuition simply fails. Yet it is not held up by fusion. It has no working furnace inside. It is a dead star that still shines because it is hot. The question is obvious. If fusion has stopped, why does a white dwarf not keep collapsing? Why does gravity not crush it further? The answer is not heat. It is quantum mechanics. Inside the white dwarf, electrons are packed into an extreme state. Electrons are fermions, and fermions obey the Pauli exclusion principle. No two identical fermions can occupy the same quantum state in the same place. When gravity tries to squeeze the matter of a white dwarf tighter and tighter, the electrons resist being forced into already occupied states. That resistance creates electron degeneracy pressure. This is not pressure in the everyday sense of hot gas bouncing against a container. It does not require a flame. It does not vanish just because the object cools. It is built into the way electrons exist. That is why a white dwarf can keep its structure even after its fusion has ended. A white dwarf is not alive, but it is not fragile. It is a corpse supported by a rule of quantum reality. There is a limit to that support. If a white dwarf becomes too massive, electron degeneracy pressure cannot hold it up. The critical value is the Chandrasekhar limit, roughly 1.4 solar masses for an ordinary carbon-oxygen white dwarf. Below that limit, the remnant can remain stable and cool for immense spans of time. Above it, the story changes. In a binary system, if a white dwarf gains enough mass from a companion, the result may be a thermonuclear runaway, a Type 1a supernova, or in some circumstances collapse toward a more compact remnant. But the quiet white dwarfs that concern us tonight stay below the limit. They do not explode. They wait. That waiting is the entire story of the black dwarf. A white dwarf has no major internal energy source left. It glows because it remembers being a star. It is like a coal taken from a furnace, except the coal is the size of a planet. The furnace was a stellar core, and the fading takes longer than the age of galaxies. Every photon that leaves the white dwarf carries away a little stored heat. Every photon makes the remnant slightly colder. Nothing replaces that energy. The cooling is one way. At first, the cooling can be relatively fast by cosmic standards. A young white dwarf may be extremely hot, glowing blue-white, bright in ultraviolet light. It can radiate enormous energy from its surface because temperature matters brutally in thermal radiation. The Stefan Boltzmann law tells us that radiated power grows with the fourth power of temperature. Double the surface temperature, and the energy emitted per unit area increases 16-fold, halve the temperature, and the output falls to 1/16. This fourth power law makes the early cooling vivid and the late cooling almost unbearably slow. A hot white dwarf pours energy into space quickly. As it cools, it radiates less. Because it radiates less, it cools more slowly. Then it radiates even less, and the cooling slows again. The process is not like descending a staircase with equal steps. It is like walking into a corridor that lengthens as you move. The closer the white dwarf gets to darkness, the longer each remaining stage takes. This is the first reason no black dwarf exists. The final cooling is not merely the last part of the journey, it is the slowest part by far. A white dwarf can fall from spectacular temperatures to a few thousand degrees over billions of years, and still be nowhere near done. That sounds counterintuitive because in ordinary life we expect cooling to be roughly proportional to temperature difference. A hot cup of coffee cools noticeably in minutes. A glowing ember dies within hours. But a white dwarf is not a cup of coffee, and space is not a kitchen. It is a star core leaking heat through a thin atmosphere into an expanding universe. The atmosphere matters more than it looks like it should. A white dwarf is not a naked ball of degenerate matter. It has a thin outer layer of ordinary, non-degenerate material, often hydrogen or helium. That layer may be tiny compared with the object as a whole, but it acts as an insulating blanket. Heat from the dense interior cannot simply appear at the surface all at once. It has to move through the outer layers. The opacity of that atmosphere, its composition, and its thickness all influence the cooling rate. A hydrogen atmosphere does not cool in exactly the same way as a helium atmosphere. The blanket is thin, but it controls the exit. Then there is crystallization. For decades, astrophysicists predicted that as a white dwarf cools, its dense interior should begin to solidify. Carbon and oxygen nuclei, once moving in a dense fluid-like plasma, gradually settle into a crystalline lattice. In ordinary language, the dead star begins to freeze. But this freezing is not like water becoming ice on a winter morning. It occurs inside matter millions of times denser than anything familiar. It is a phase transition in a strongly coupled plasma, under conditions that no laboratory can reproduce in full. When a substance crystallizes, it releases latent heat. Water releases heat when it freezes. The same basic idea applies here, though the environment is far more extreme. As a white dwarf crystallizes, latent heat is released inside it. That heat has to escape before the remnant can continue cooling. The freezing of the star delays the death of its glow. There is an additional complication. The interior is not perfectly uniform. During crystallization, oxygen-rich material can become concentrated in the solid phase, while carbon-rich liquid remains above it. Heavier oxygen-rich crystals tend to sink. Lighter carbon-rich material can rise. This slow chemical separation releases gravitational energy because denser material moving inward lowers the system's gravitational potential energy. That energy becomes heat. Once again, the white dwarf is delayed on its path to darkness. So the white dwarf is not simply cooling like a stone in the night. It is cooling while changing phase. It is cooling through an insulating envelope. It is cooling while its internal composition rearranges itself. Each effect has a scientific mechanism. Each effect has observational consequences. Each one makes the road to black dwarf longer. And this is where the first real counterargument enters. Someone could reasonably say, if black dwarfs have never been observed, why speak of them with such confidence? Why not call them a guess? That objection matters. Science should not treat unobserved future objects the same way it treats observed ones. A black dwarf is not a cataloged star. It has no measured spectrum. It has no location. It has never appeared in a telescope image. We should not pretend otherwise. The answer is that black dwarfs are not invented as a separate speculative species. They are the extrapolated end of a process already observed. White dwarfs exist. They cool. Their cooling sequences can be measured in populations of stars. Their physics is constrained by thermodynamics, quantum mechanics, stellar evolution, and observations. We see hot white dwarfs, warm white dwarfs, cool white dwarfs. We see the curve. We see the delay from crystallization. We see the population aging. What we do not see is the final endpoint, because the timeline is too long. The strongest language we should use is not that black dwarfs are observed, but that they are the expected future state of isolated white dwarfs, if known physics continues to apply and no other process destroys them first. That last phrase matters. If known physics continues to apply and no other process destroys them first. This is where the story becomes more interesting than the simple version. A black dwarf is not just a future object. It is a bet on deep time. It assumes that matter remains stable long enough, that protons do not decay on a shorter time scale, that the white dwarf is not disrupted by collisions, mergers, or accretion, and that the universe continues expanding in a way broadly consistent with our current models. The black dwarf is likely in standard stellar evolution, but its far future depends on assumptions we cannot directly test across quadrillions of years. For the ordinary formation of black dwarfs, the timescales are already extreme. The current universe is about 13.8 billion years old. That sounds ancient, and compared with human history it is. But if the first true black dwarfs require something like a quadrillion years or more, then the universe is not middle-aged in this story. It is barely past infancy. The entire age of galaxies so far is only a tiny fraction of the waiting period required for the first white dwarfs to become essentially dark. This mismatch changes the emotional scale of the subject. The black dwarf is not just a cold object. It is an object that exposes how young the universe still is. We think of cosmic history as immense because it contains the Big Bang, the first stars, the formation of heavy elements, the birth of the Milky Way, the formation of Earth, the emergence of life, and the entire history of human beings. But black dwarfs tell us that everything we call cosmic history so far is only the opening paragraph of a much longer book. If the cooling time were compressed into a year, the present universe would not be late December. It would not be autumn. It would be the first few minutes after midnight on January 1st. Stars have been born and died. Galaxies have merged. Civilizations may have risen somewhere in the dark, and still the black dwarf clock has barely begun. This is the central thesis of the account. The most important fact about black dwarfs is not that they will be dark, but that they reveal a universe where prediction can outrun observation by a gulf of time so vast it becomes philosophical. We are describing a physical object that is real in the equations, inevitable in the standard story, and absent from reality today. That tension is the reason black dwarfs are more than a footnote in stellar evolution. The easiest way to misunderstand them is to imagine that a black dwarf is simply invisible and therefore uninteresting. But invisibility is precisely what makes the object powerful. Most astronomical objects announce themselves by radiation. A star shines, a nebula glows, a pulsar ticks. A black hole reveals itself when matter heats around it, or when gravity distorts its surroundings. A black dwarf, once formed, would do almost nothing. It would carry mass, gravity, history, and structure, but almost no light. It would be a stellar remnant that has spent its thermal inheritance. If you could approach one in the far future, you would not see a glowing sphere. You might notice only the absence of background light where the object blocks distant stars, assuming there were still distant stars bright enough to block. You might detect its gravity if something orbited it. You might see it lens a background source, but the object itself would be nearly indistinguishable from darkness. It would be a star that has become a gravitational fact rather than a visible one. Its size would remain roughly planetary. Its mass would remain stellar. Its surface gravity would remain crushing. Its structure would remain supported by electron degeneracy pressure. Cooling to darkness does not make it evaporate. It does not make it collapse. Temperature is not what holds it up. Quantum mechanics does. That is one of the most beautiful parts of the story. A black dwarf can be cold and still stable. It can be dark and still massive. It can be nearly invisible and still be one of the densest ordinary objects in the universe. This separates it from a black hole. The names sound similar, but the physics is entirely different. A black hole is a region of space-time where gravity has created an event horizon, a boundary beyond which light cannot escape. A black dwarf has no event horizon. It does not trap light by making escape impossible. It simply has no meaningful light of its own to give. If you shone a beam at it, light could reflect or scatter depending on its surface properties. In principle, information could leave. A black dwarf is not a prison for light. It is a burned-out ember. It is also not a brown dwarf. A brown dwarf is a substellar object that formed like a star but never achieved sustained hydrogen fusion. It is sometimes called a failed star, though that phrase is more poetic than precise. A black dwarf, by contrast, was once the exposed core of a real star that completed its main nuclear life and became a white dwarf. A brown dwarf is too small to become a true star. A black dwarf is the ancient remnant of a star that once truly shone. These distinctions matter because astronomy has too many dwarf names, and not all darkness is the same. A brown dwarf is dim because it never became a main sequence star. A white dwarf is bright because it is hot, leftover core matter. A black dwarf is dark because a white dwarf has had enough time to cool almost completely. A black hole is dark because space-time itself prevents escape from inside the horizon. The word black hides several different physical meanings. Science becomes clearer when we force the words to explain themselves. Now we need to move from the object to the cosmic era in which it matters. Today we live in the stelliferous era, the age of stars. The universe is bright because fusion is still happening. Massive stars live fast and die violently. Sun-like stars live for billions of years. Red dwarfs live far longer, perhaps trillions of years, because they burn hydrogen slowly and efficiently. Star formation is still happening, but not as intensely as it did in the younger universe. Galaxies are aging. Gas reservoirs are being consumed. The great star-forming peak lies in the past. Eventually, the supply of cold gas available for new stars will decline so far that star formation effectively ends. The last normal stars to shine will likely be small red dwarfs, because they are the most economical burners in the stellar population. They can live for trillions of years. In the far future, after more massive stars are long gone, red dwarfs will be the final lamps of the universe, faint, red, patient, and numerous. But even red dwarfs are not eternal. When the last of them exhaust their fuel, the age of starlight ends. What remains is not nothing. The universe will still contain matter. It will contain white dwarfs, neutron stars, black holes, brown dwarfs, planets, and eventually black dwarfs. But the matter will no longer be arranged in living stars that generate new light by fusion. This is the degenerate era, an age dominated by remnants. Black dwarfs belong to that era. They are not curiosities at the edge of the story. They may become one of the most common large objects in the far future, because most stars are not massive enough to end as neutron stars or black holes. Most stars are small enough to end as white dwarfs, and most white dwarfs, if left alone, cool toward black dwarfs. The dramatic deaths make the headlines, but the quiet deaths win by number. This is another important controversy. Human attention is biased toward cosmic violence. We remember supernova, gamma-ray bursts, black holes, neutron star mergers, and the first images of accretion around event horizons. They feel like the universe showing its power. But the far future is not dominated by explosions. It is dominated by cooling. The most common fate is not fire. It is fading. The universe is not only a machine for making spectacular endings, it is also a machine for making long silences. A black dwarf is that silence turned into an object. It is the afterlife of ordinary starlight. It says that the majority story of stars is not the short, brilliant catastrophe, but the patient loss of heat. If we follow the timeline farther, the picture becomes almost impossible to hold in the mind. Galaxies themselves are not permanent structures. Over enormous spans of time, gravitational encounters between stellar remnants can eject many objects into intergalactic space. Others may fall inward toward central black holes. The familiar shape of a spiral galaxy will not remain. There will be no blue arms rich with star formation, no glowing nebulae, no young clusters. There will be remnants scattered through a darkening gravitational landscape. Black dwarfs in such an era would drift through space mostly unseen. They might occasionally pass near other remnants. Some might collide or merge. Some might be ejected from former galaxies entirely. Some might remain bound to companions. But the general trend is toward isolation and darkness. The universe expands. Distances grow. Background radiation cools. Events become rarer. The clock continues, but almost nothing visible marks its ticking. The cosmic microwave background also matters here. Today, the background radiation fills the universe at about 2.7 Kelvin. A white dwarf cannot cool below its surroundings. It is immersed in that radiation bath. But as the universe expands, the background photons stretch, their temperature falling. The floor drops. The white dwarf continues cooling toward that moving floor. A true black dwarf is not necessarily absolute zero, because absolute zero is an unattainable ideal. It is more practically a white dwarf that is cooled until it emits no significant net radiation against the cosmic background. It has joined the temperature of the dark. The phrase black dwarf therefore contains an approximation. It does not mean a perfect object at exactly 0 Kelvin. It means a former white dwarf, so cold and so faint that, for astrophysical purposes, it no longer shines. This is careful language. It matters because a careless account might say black dwarfs are completely frozen at absolute zero. The safer scientific statement is that they cool toward thermal equilibrium with an ever colder universe, becoming effectively dark. There is another far future possibility, and this one must be handled with even more care. Some theoretical work has explored whether black dwarfs, after fantastically long times, might undergo one last transformation through quantum tunneling. In ordinary stars, fusion requires high temperatures because positively charged nuclei repel each other. They need enough energy to overcome the Coulomb barrier and get close enough for the strong nuclear force to bind them. In a cold black dwarf, the thermal energy is gone. Classical fusion seems impossible, but quantum mechanics allows tunneling. Particles can sometimes pass through barriers. They do not have enough energy to climb over in the classical sense. This is not magic. It is a well-tested feature of quantum theory. It explains radioactive decay and plays a role in the fusion that powers stars. In the dense crystal of a black dwarf, carbon and oxygen nuclei might very rarely fuse by pycnonuclear reactions driven by density rather than heat. The rate would be unbelievably low. But in a universe that waits long enough, even fantastically unlikely processes can accumulate. The provocative idea is that some sufficiently massive black dwarfs might slowly convert their material toward heavier elements, eventually building enough iron-rich matter to destabilize themselves. If the right conditions are met, they might collapse or explode in events sometimes called black dwarf supernovae. These would not occur in any meaningful near future. The timescale proposed is so large that it exceeds the number of particles in the observable universe by absurd margins when written as powers of 10. We are not talking about waiting trillions of years. We are talking about numbers like 10 to the power of 1100 years. The image is irresistible. After a universe of darkness, the last explosions come from black dwarfs that finally destroy themselves through quantum tunneling. But the strongest counterargument must be given honestly. This scenario depends on assumptions. It assumes that protons do not decay on shorter timescales. It depends on extremely uncertain pycnonuclear reaction rates in cold, dense matter. It applies only to certain masses and compositions, not necessarily every black dwarf. It is a serious theoretical possibility, not an established future event. This is where science-safe controversy matters most. A weak version of the story would say black dwarfs will definitely explode as the final supernova of the universe. A careful version says that if proton decay does not occur, and if dense matter tunneling proceeds as certain models estimate, then some massive black dwarfs may undergo far future explosions that could be among the last energetic astrophysical transients. The cautious version is less sensational but more powerful because it lets the wonder survive without pretending the uncertainty is gone. Proton decay is itself an open question. The standard model of particle physics does not require ordinary protons to decay in the way many grand unified theories predict. Experiments have searched for proton decay and have not confirmed it. If protons are absolutely stable, black dwarfs can persist for unimaginably long times. If protons decay on timescales far shorter than the black dwarf supernova timescale, then matter inside black dwarfs would gradually disintegrate before any such final explosion could happen. The far future branches depending on physics we have not yet settled. That uncertainty is not a weakness of the story. It is the story. The black dwarf forces us to separate layers of confidence. We are highly confident that white dwarfs cool. We are confident that no black dwarfs exist yet, because the universe is too young. We expect black dwarfs in the far future, under standard assumptions. We are much less certain about what happens to them after absurdly longer times, because proton stability, dark matter interactions, cosmic expansion, and dense matter tunneling all become relevant. The farther we project into time, the more the story becomes a map of our assumptions. This is why black dwarfs make better science documentary material than they first appear to. They are not flashy. They do not tear space-time open. They do not beam radio pulses like neutron stars or bend light from inside an event horizon. But they ask a sharper question. How far can physics responsibly see into the future? Can we speak of objects that do not exist yet? When is a prediction strong enough to deserve a name? And when does certainty become overreach? The answer depends on what kind of claim we are making. If we claim that the current universe contains black dwarfs, we are wrong. If we claim that isolated white dwarfs should cool toward black dwarf states over immense time, we are standing on well-established physics. If we claim that some black dwarfs may eventually explode after times like 10 to the 1100 years, we are describing a model-dependent theoretical possibility. If we claim that this is guaranteed, we have gone too far. The account must keep those boundaries visible. Let us return to the present for a moment, because the present is where the evidence lives. Astronomers use white dwarfs as cosmic clocks. Since white dwarfs cool predictably, the faintest and coolest white dwarfs in a star cluster can help estimate the age of that population. The method is not simple, because cooling depends on mass, atmosphere, composition, crystallization, and other effects, but it is powerful. Dead stars become timepieces. This is a beautiful reversal. A white dwarf no longer produces energy by fusion, yet it produces information. Its fading light tells us how long it has been cooling. A cluster of white dwarfs reveals the age of a stellar population. The very slowness that prevents black dwarfs from existing today allows astronomers to measure cosmic time. The delay is not just an obstacle, it is a tool. The Gaia mission strengthened this story by measuring precise distances and brightnesses for enormous numbers of stars, including white dwarfs, near the Sun. In the Gaia color magnitude data, astronomers found evidence for a pileup in the white dwarf cooling sequence, a sign that many white dwarfs were spending extra time at certain luminosities. The interpretation was crystallization. The release of latent heat and gravitational energy slows the cooling. The theoretical prediction left a fingerprint in the population. This is exactly the kind of evidence chain the topic needs. Claim: white dwarf cooling is delayed. Mechanism: crystallization releases heat, and sedimentation releases gravitational energy. Evidence: the Gaia pileup. Limitation: models still differ in details. Consequence: the road to black dwarf is even longer and more measurable than a simple cooling curve would suggest. The coldest known white dwarfs are the closest things we have to black dwarfs, and they are still warm by ordinary standards. Some ancient white dwarfs are faint and cool compared with typical stars, but their surfaces remain thousands of degrees above absolute zero. They emit light, often weakly, often in infrared, but they are not dark. They have cooled for nearly the age of the universe and remain visibly unfinished. That fact should change how we hear the phrase dead star. Dead does not mean over. In astronomy, death can be active, radioactive, gravitational, thermal, or quantum. A neutron star is dead in the sense that it is no longer a normal fusion-burning star, yet it can pulse, flare, glitch, and merge. A white dwarf is dead in the sense that fusion has stopped, yet it can shine for billions of years, crystallize, accrete, explode in a binary, or become a cosmic clock. A black dwarf is the quieter end of that path, dead enough not to shine, but still physically present. Imagine the future sun as a white dwarf. Not tomorrow, not soon, not on any human scale. Billions of years from now, after the sun has left the main sequence, expanded, transformed the inner solar system, and shed its outer layers, a small hot core will remain. That remnant will glow at first. It will illuminate the debris of its own final exhalation. Then the nebula will disperse. The white dwarf will cool. Planets, if any remain, will orbit a dimming stellar corpse. The remnant of our sun will spend far longer cooling than the sun spent supporting life on Earth. Eventually, in a universe unimaginably older than the present, the solar white dwarf should become a black dwarf. The star that once powered weather, oceans, photosynthesis, and human vision would become a cold, dark mass, still there but no longer giving. It is difficult to imagine a more complete reversal. The source of daylight becomes an invisible relic. Yet this future does not make the present meaningless. It makes the present rare. We live during the era when stars still shine, when white dwarfs are still warm, when galaxies are still visible, when the cosmic microwave background is still relatively warm by future standards, when chemistry, planets, and perhaps life are possible in forms we recognize. The black dwarf is a reminder that the age of light is temporary. It does not cheapen the light. It makes it precious. Now consider detection in the far future. If black dwarfs fill the remnants of galaxies, how would any hypothetical observer find them? They might watch for gravitational effects. A black dwarf in a binary could reveal itself through an unseen mass pulling on a companion. A black dwarf passing in front of a distant source could cause microlensing, briefly magnifying background light. A population of black dwarfs could influence the dynamics of a remnant galaxy. But the objects themselves would be nearly silent. They would be known by what they do to other things, not by what they emit. This is not entirely alien to astronomy. Much of the universe is known indirectly. Dark matter is inferred from gravity. Exoplanets are often found by tiny dips in starlight or stellar wobbles. Black holes are detected by orbits, accretion, jets, gravitational waves, or shadows. Not by light from inside the horizon, but black dwarfs would represent a particularly quiet form of indirect existence. They would not be exotic engines. They would be spent engines. There is something almost humbling about that. The far future universe may contain enormous amounts of matter that no longer announces itself. The cosmos does not become empty all at once. It becomes dark while still full. It becomes populated by things that have histories, but no glow. A black dwarf is not absence. It is presence without radiance. And that idea creates the emotional spine of the documentary. The comfortable belief says the universe is defined by what shines. The pressure point says most of the future belongs to things that do not. The strong claim is that black dwarfs may be the most important stars that do not yet exist, because they reveal the long-term destiny of ordinary stellar matter. The counterargument is that they are unobserved, and their deepest future depends on unresolved physics. The limitation is that we can predict their cooling more confidently than their final fate. The consequence is that the universe's story is not just a history of light, but a history of light gradually losing the argument to time. We should be careful with the phrase final fate. In a universe where protons decay, even black dwarfs may not persist forever. In a universe where black dwarfs collide, merge, or are consumed by black holes, individual remnants can have different endings. In a universe with dark energy driving accelerating expansion, many regions become causally isolated. The future is not one simple scene. It is a tree of possibilities. But the broad thermal story remains. White dwarfs cool, and cooling leads toward darkness unless some other process intervenes. Another common mistake is to make the black dwarf sound like a frozen planet. It is not a planet. Its radius may be Earth-like, but its mass and interior physics are stellar. It is degenerate matter, not ordinary rock. Its surface gravity would be lethal beyond comprehension. The crystalline structure inside it is not like a diamond you could hold. It is a star core in a quantum-supported state. If we use earthly metaphors, they must be bridges, not replacements. A black dwarf may be cold, but cold does not mean delicate. It may be dark, but dark does not mean empty. It may be silent, But silent does not mean simple. It is one of the most compressed forms of ordinary stellar history. Inside it is the record of a star's life, the hydrogen it once burned, the helium it fused, the carbon and oxygen it built, the mass it lost, the envelope it shed, the long cooling it endured. It is biography without light. This is why the phrase "an object that does not exist" is not a gimmick. It is scientifically precise if used carefully. Black dwarfs do not exist now, as far as standard astrophysics tells us, because the universe is too young. Yet the category is meaningful, because it describes the future state of objects already on the path. The non-existence is temporal, not physical. The laws do not forbid black dwarfs. The clock has not reached them. In a way, astronomy is always dealing with time displacement. When we look at distant galaxies, we see them as they were, not as they are now. When we study the cosmic microwave background, we see the universe as it was when it became transparent. When we study white dwarfs, we see dead stars at different stages of cooling. But black dwarfs are different. They are not an old light arriving late. They are a future darkness that has not happened yet. That future darkness should not be portrayed as immediate doom. It is not a threat to Earth. It is not a warning about tomorrow. It is not a disaster narrative. The black dwarf is too slow for fear. It belongs to a timescale where fear becomes meaningless. What it offers is perspective. It stretches the mind past the short attention span of living beings and forces us to confront the patience of physics. When we say the universe is old, we usually mean it is old compared with us. Compared with black dwarfs, it is not old. Compared with black hole evaporation, it is not old. Compared with possible black dwarf supernovae in a no-proton decay future, it is less than a blink. Cosmic time is not one scale. It is a hierarchy of scales, and black dwarfs occupy a region so far beyond ordinary astrophysical lifetimes that even galaxies feel temporary. This is where the account must slow down. Not to repeat the same point, but to let the public feel the proportions. A human life is a century. Civilization is thousands of years. Complex life is hundreds of millions. Earth is 4.5 billion. The universe is 13.8 billion. Red dwarfs may live trillions. Black dwarfs may require quadrillions or more. Black holes may evaporate after times written with dozens or 100 zeros. Possible black dwarf supernovae, if they occur, belong to numbers with more than 1,000 zeros. Each step is not just bigger, it is a new kind of time. And still, the mechanism is simple. Heat leaves, photons escape, matter rearranges, the background cools, the star fades. The simplicity is part of the awe. The longest process in the future of ordinary stars is not complicated by drama. It is the same kind of physical accounting that cools a stone, extended into a regime where quantum mechanics and stellar density dominate. The universe does not need to do something spectacular to build black dwarfs. It only needs to wait. Waiting, however, is not nothing. In physics, waiting can be creative. Given enough time, unlikely events become possible. Given enough time, gravitational encounters reshape galaxies. Given enough time, black holes evaporate. Given enough time, quantum tunneling may alter the cores of black dwarfs. Deep time is an active ingredient. It changes what possible means. This is perhaps the most controversial idea in the whole subject. Impossibility often has an expiration date. Carbon fusion in a cold black dwarf is impossible in the ordinary thermal sense. But if quantum tunneling is allowed, and the object persists long enough, impossible becomes rare, and rare becomes eventually. The difference between never and almost never is small in daily life. In a universe with timescales like 10 to the 1100 years, it can become enormous. But again, this must be framed as conditional. Deep time does not make every fantasy real. It makes physically allowed rare processes relevant. There is a difference. Quantum tunneling is real. Nuclear fusion is a legitimate concept in dense matter, but the exact rates and outcomes in black dwarfs remain theoretical. The science-safe stance is not to deny the possibility and not to oversell it. It is to show the structure of the argument and the points where uncertainty enters. The same approach applies to proton decay. If protons decay, then the long-term survival of black dwarfs changes radically. The black dwarf may never get to its hypothetical supernova phase, because the baryonic matter inside it would decay first. If protons are stable, black dwarfs can survive into the extreme far future. Observationally, proton decay has not been found, but non-detection is not the same as proof of absolute stability. We know lower limits. We do not know eternity. A thoughtful observer could therefore disagree with the strongest far future claims. They could say, black dwarfs as cooling endpoints are reasonable, but black dwarf supernovae are too speculative to present as destiny. That observer would be right to object if the account claimed too much. The fair answer is that the ordinary black dwarf is a robust expectation, while the black dwarf supernova is a conditional far future hypothesis. The tension is not a problem. It is a way to keep the science honest. What makes this story powerful is that it contains both firmness and humility. Firmness. White dwarfs cool. The universe is too young for black dwarfs. The physics of degenerate matter explains why white dwarfs remain stable. Crystallization delays cooling. Humility. Exact cooling times vary. The farthest future depends on physics we have not fully tested. Some imagined endings may fail if proton decay exists, or if dense matter reaction rates differ from the models. The strongest documentary voice is not the one that sounds certain about everything. It is the one that knows where certainty ends. Let us imagine the population of the future. The last red dwarfs have died. The last star-forming gas has been consumed or dispersed. The sky contains no familiar stars. Former galaxies have become dim graveyards of remnants. White dwarfs, one by one, cool below detectability. Black dwarfs multiply. The universe is not empty, but it is no longer luminous. It has become an archive written in gravity. If an observer existed then, they would not navigate by constellations. The constellations would be gone. They would not see the Milky Way as a river of light. They might infer structure through gravity, through relic motions, through rare lensing events, through the occasional merger or decay. Knowledge in such a universe would be harder because the universe would offer fewer signals. The age of stars is not only the age of light, it is the age of information. That is a subtle consequence. When the universe goes dark, it does not merely become less beautiful to look at, it becomes harder to know. Light is the messenger that allows astronomy. We study the cosmos because photons, neutrinos, cosmic rays, and gravitational waves carry information. In the degenerate era, many messengers become rarer. If intelligent life arose extremely late, after starlight faded, its universe would be poorer in evidence. It might never know the bright past. It might live among black dwarfs and not understand that they were once stars. This idea should not be pushed into fantasy, but it has philosophical weight. We are fortunate to live in a time when the universe is readable. The cosmic microwave background still exists. Galaxies still shine. Stars still form. White dwarfs are visible. Supernovae still occur. The evidence of cosmic history is still written in light. A far future observer may inherit a darker library with many pages burned away. Black dwarfs therefore connect to a larger question. Is our cosmic era special for knowledge? Not special in a mystical sense, but observationally special. We live after enough time has passed for heavy elements, planets, and life, but before too much time has passed for the sky to go dark. The window for observers like us may be limited. The black dwarf is what waits beyond that window. Now let us return to scale. A white dwarf may cool for a quadrillion years before it becomes a black dwarf. A quadrillion is a 1 followed by 15 zeros. It is not just a big number. It is a number so large that human language treats it as decoration. But physics does not. Physics has no difficulty with long time. The equations do not grow impatient. If a process takes a quadrillion years, then it takes a quadrillion years. The universe does not care that the number is emotionally inconvenient. That indifference is part of the shock. Human beings evolved for days, seasons, decades. Our sense of time is biological. The cosmos operates with no obligation to fit that sense. A star can live for 10 trillion years. A remnant can cool for a quadrillion. A black hole can evaporate over a Google years. Possible quantum processes can wait for numbers that make a Google look small. The universe does not merely dwarf us in space, it dwarfs us in duration. Yet this does not mean we are irrelevant. Understanding a black dwarf requires mathematics, observation, and imagination. A species living for a century can describe a process lasting quadrillions of years. That is one of the quiet miracles of science. We cannot wait for a black dwarf, but we can infer it. We cannot observe the endpoint, but we can understand the curve. Our lives are short, but our reasoning can reach into eras where no living witness may ever stand. That is why black dwarfs are not depressing. They are humbling, but also astonishing. They show that the mind can travel where the body cannot, and where time itself will not take us. They show that science is not only a catalog of objects, but a disciplined way of extending knowledge beyond immediate experience. We know the black dwarf by following energy, pressure, matter, and time. There is another reason the black dwarf story deserves a careful voice. It sits at the intersection of two kinds of time: stellar time and thermodynamic time. Stellar time is the time of burning, the time measured by fuel consumption. A massive star burns through its life in millions of years. A sun-like star burns through its life in billions. A red dwarf may burn for trillions. But once fusion ends, the star's clock changes. It is no longer counting fuel reactions. It is counting heat loss. The pace is no longer set by nuclear burning in a core, but by the slow ability of a dense remnant to leak energy through its surface. That transition from burning to cooling is more than an astrophysical detail. It is a change in the meaning of time. During the main sequence, the star has a central engine. During the white dwarf phase, it has memory. The white dwarf shines because the past is still warm. A black dwarf is what remains when the past has cooled enough to stop speaking in light. In that sense, it is not merely the future of a star. It is the exhaustion of a star's memory. This also explains why white dwarfs are so valuable to astronomers today. They are not only endpoints, they are clocks. In a young stellar population, the white dwarf sequence still contains many hot remnants. In an old population, the sequence extends to cooler and fainter objects. The faint end of that sequence marks how long the oldest white dwarfs have been cooling. By comparing observed populations with cooling models, astronomers can estimate the ages of star clusters, the disk of the Milky Way, and ancient stellar populations. The dead stars become a timekeeping system for the galaxy. But this clock is only as good as the physics inside it. If crystallization releases latent heat, the clock slows. If oxygen settles inward and carbon rises outward, the clock slows again. If trace elements like neon sediment through the interior, the clock can shift. If the atmosphere is hydrogen-rich instead of helium-rich, the heat escapes differently. These are not decorative details. They change age estimates. They are why white dwarf cooling remains an active research field rather than a solved classroom exercise. That is another useful counterweight to the simple story. A popular version might say, white dwarfs cool, therefore black dwarfs form after a fixed number of years. A careful version says, white dwarfs cool along tracks that depend on mass, composition, atmosphere, crystallization, sedimentation, and the changing cosmic background. The destination is simple. The road is not. Even the word cool can be misleading if it makes the process sound passive. At the level of the population, cooling creates structure in data. At certain temperatures, white dwarfs linger because internal energy is being released by phase transitions. That lingering creates a pileup in a color magnitude diagram. The diagram is not just a plot. It is a fossil record of physics occurring inside dead stars. The white dwarfs pause, not because they choose to, but because the interior is crystallizing and releasing heat. A star can announce its internal freezing by the way it slows down its fading. The black dwarf, then, is not reached by a smooth slide alone. It is approached through bottlenecks. Thermal radiation slows with temperature. Atmospheres insulate. Crystallization pays out hidden heat. Chemical separation converts gravitational rearrangement into additional warmth. Quantum-specific heat changes at low temperature. The cooling curve contains chapters. Each chapter delays the darkness. This layered cooling also helps us avoid another exaggeration, that all black dwarfs will be identical. They will share the general property of being cold, degenerate remnants, but their masses, compositions, histories, and environments will differ. A black dwarf descended from a low-mass carbon-oxygen white dwarf will not be exactly the same as one descended from an ultramassive oxygen neon white dwarf. A black dwarf that spent time in a binary system will not have the same history as one that drifted alone. Some may have thin hydrogen layers. Some may have helium atmospheres. Some may have accreted planetary debris in their white dwarf phase. The darkness hides variety. That hidden variety is important for the far future supernova question. Not every black dwarf would be a candidate for such an event. The theoretical picture favors more massive remnants where pressures are higher, and dense matter fusion by tunneling is more effective. Lower mass black dwarfs would evolve even more slowly, and many may never reach the same instability before other unknown long-term processes intervene. The phrase black dwarf supernova should not be heard as the fate of all black dwarfs. It is a possible fate for some under specific assumptions, and those assumptions are enormous. They require the object to persist through times that make ordinary cosmic eras look momentary. They require the nuclei inside the black dwarf to keep participating in rare quantum processes. They require matter itself to remain available for those processes. They require no faster decay mechanism to erase the star first In a documentary voiceover, this is exactly where temptation appears. The image of the last supernova is so powerful that it wants to become certainty. But science does not owe us the most cinematic ending. The more honest ending is stranger. The universe might end with black holes evaporating into faint radiation. It might contain proton decay that erases ordinary matter. It might permit black dwarf supernovae as rare final flashes. It might have aspects of dark energy or fundamental physics that change the long-term picture in ways we cannot yet calculate. The black dwarf stands inside this uncertainty. It is a robust, near-far future expectation compared with the present age, and a fragile, ultra-far future platform for speculation. That distinction gives the topic its intellectual tension. The black dwarf is both one of the safest predictions in ordinary stellar cooling and one of the gates into the least testable regions of cosmic futurism. The same object that follows from basic thermodynamics also leads us toward questions about proton stability and the fate of matter after times no experiment can simulate. It is a bridge from undergraduate physics to the edge of metaphysics, but it must be crossed with discipline. Consider the role of observation again. We cannot observe a black dwarf, but we can observe the absence of black dwarfs. That absence is not a failure. It is evidence consistent with the timeline. If black dwarfs were found today, standard stellar evolution would face a crisis because the universe should not have had enough time to make them. A confirmed black dwarf in the present universe would be more shocking than the lack of one. It would mean either our cooling models were badly wrong, the object had an exotic origin, or the age and history of the universe required radical revision. The fact that we do not see black dwarfs is exactly what the theory expects. This is a subtle but important scientific point. Non-detection is not always ignorance. Sometimes non-detection is a successful prediction. We do not see black dwarfs because they should not yet exist. The absence itself tells us that the cooling times are long. The universe is young relative to them, and the standard picture remains coherent. In that sense, the empty catalog entry for black dwarfs is meaningful. The same absence also protects us from overclaiming. Since no black dwarf exists, every description of its appearance is conditional. We can infer size, mass, temperature, and detectability from the properties of its white dwarf ancestor and from cooling physics. But there is no black dwarf spectrum to show. There is no measured surface composition. There is no observed population distribution. The account must speak as a guide to a future landscape, not as a travelogue from a place already visited. The most powerful image may be that the universe is manufacturing invisibility. A star begins as a luminous object, turning mass into light. It ends as a remnant that gradually loses the ability to be seen. Across cosmic time, the universe converts visible stellar history into dark gravitational memory. Black dwarfs are not just cooled stars. They are stored mass without the radiance that once made that mass part of the visible cosmos. This changes the meaning of darkness. We often imagine darkness as empty space, but the far future may be dark because it is full of objects that no longer shine. Darkness can be crowded. It can contain black dwarfs, cold planets, neutron stars, black holes, and debris, all drifting without illumination. A dark universe is not necessarily a universe with nothing in it. It is a universe where matter has stopped advertising itself. That is why black dwarfs are worth discussing even before they exist. They train us not to confuse visibility with importance. The future may be governed by objects that are almost impossible to see. Their lack of light will not make them irrelevant. Their gravity will remain. Their histories will remain. Their existence will shape whatever remnants of structure survive. And finally, black dwarfs force us to think about endings without spectacle. Human imagination gravitates toward apocalypse as a bright event, a final fire, a dramatic collapse. But the most common stellar ending may be closer to a whisper, stretched over quadrillions of years. The ordinary stars do not all die with a scream. Most fade so slowly that the word event becomes inappropriate. Their ending is not a moment. It is an era. This is why the documentary must not turn black dwarfs into monsters. They are not threats. They are not cosmic villains. They do not rush toward us. They do not announce the death of the universe tomorrow. They are the opposite of urgency. They are what happens when urgency has been exhausted. They are the patient future of matter after fire. In the end, the black dwarf is a paradox with a simple resolution. It is an object that does not exist because the universe is too young. It is an object that should exist because white dwarfs cool. It is an object that may dominate the far future because most stars die quietly. It is an object whose ultimate fate is less certain because deep time invites physics we have not yet confirmed. Every part of that statement is necessary. Remove the first part, and you overstate observation. Remove the second, and you lose the physics. Remove the third, and you lose the cosmic consequence. Remove the fourth, and you lose honesty. The truth is not a single dramatic sentence. It is a structured tension. So imagine a white dwarf tonight, somewhere in the halo of the Milky Way, faint, ancient, and cooling. It may have formed before the sun existed. It may have watched generations of stars form and die around it. It has no fusion left. It is supported by electrons that refuse to collapse into identical quantum states. Its core may be crystallizing. Its atmosphere may be leaking heat with terrible slowness. It is dimmer than it once was, but still not dark. After billions of years, it is still glowing. That glow is the difference between the universe we have and the universe to come. For now, the light persists. The oldest white dwarfs are not black dwarfs. The final darkness has not arrived. The cosmic ember is still warm. One day, if the universe continues along this path, that ember will cool beyond visibility. The remnant will stop being a white dwarf in any meaningful visual sense. It will become a black dwarf, a star corpse that has finally spent its heat. It will drift through a universe with fewer lamps, fewer signals, fewer witnesses, and more silence. And if the most speculative far future models are right, some of those black dwarfs may eventually find one last way to change, through the faint arithmetic of quantum tunneling after a duration too large to imagine. But even if that never happens, even if proton decay erases the possibility, even if the final explosions remain only a mathematical branch, the ordinary black dwarf remains enough, because the ordinary black dwarf already tells us the hardest truth. The universe is not finished becoming what it will be. The objects that dominate the far future may not exist yet. The sky we see is temporary, not because the stars are unimportant, but because they are part of a longer thermodynamic story. Light is a phase. Heat is an inheritance. Darkness is not emptiness. It is what remains after energy has finished speaking. Tonight, every star you see is somewhere on a path. Some will die violently. Some will collapse. Some will fade. The most massive will leave neutron stars or black holes. The ordinary majority will leave white dwarfs. And those white dwarfs will cool across ages that make the present universe seem impossibly young. None has reached the black dwarf state. Not one. The cosmos has been working on them since the first white dwarfs formed, and it is not close to done. That is the true scale of a black dwarf, not its size, though it may be Earth-sized and star-massed, not its darkness, though it will be nearly invisible, not even its coldness, though it will approach the background temperature of an aging universe. Its true scale is time. A black dwarf is what happens when a star's death is measured not in seconds like a supernova, not in millions of years like stellar evolution, not even in billions like galaxies, but in quadrillions and beyond. It is the universe's most patient creation, a thing with a name, a theory, a mechanism, and no examples. A future fossil of ordinary starlight. A promise written by thermodynamics and delayed by the youth of the cosmos. A reminder that the universe can be full of things that are inevitable and still not yet real. For now, the black dwarfs are absent, the white dwarfs are still glowing, the stars are still burning, the age of light has not ended. We live before the silence, before the long, dark archive, before the cold stellar embers have finished fading. And that means that when you look up, you are not merely seeing stars. You are seeing a temporary victory over time. The light is still here. The dead stars are still warm. The future has not yet caught up with the equations. Somewhere, all across the universe, white dwarfs are cooling one photon at a time. And every photon they lose is a step toward an object no one has ever seen, an object that does not exist tonight, but waits in the mathematics of the far future. The star is gone, but the accounting of its heat continues, quieter than silence and longer than memory. That is why the absence of black dwarfs is not empty trivia. It is a measurement of cosmic youth. It tells us that even the oldest stellar remnants have not had enough time to finish their cooling. It tells us that the universe has produced dead stars, but not yet the final form of ordinary stellar death. And it tells us that the future will be populated by objects whose existence is written less in brightness than in patience. That object is the black dwarf, the star that has not happened yet. There is one more way to feel the difference between a black dwarf and every star we know. A star is visible because energy is moving outward through it. Somewhere inside, or from some stored reservoir, heat is being delivered to the surface and then to space. The surface is a conversation between interior and universe. A black dwarf is the end of that conversation. It still has a surface. It still has gravity. It still occupies space. But the energy difference that made it visible has nearly vanished. It has become thermodynamically quiet. Thermodynamic quiet does not mean absolute peace. The object still sits in a universe where gravity acts, where particles may decay if nature allows it, where quantum tunneling may occur, where rare encounters can disturb an otherwise silent remnant. But compared with a star, compared with a young white dwarf, compared with the violent machines that dominate astronomy headlines, a black dwarf is almost motionless in the public imagination. Its drama is not movement. Its drama is the absence of movement after a history of fire. This is why the name black dwarf can mislead. It sounds like a smaller version of a black hole or a cousin of a brown dwarf, something exotic because it is dark. But the real exotic feature is not the darkness alone. It is the fact that darkness took so long to arrive. A black dwarf is not born black. It earns its darkness by cooling across eras. It is the result of a debt paid one photon at a time. Every photon matters in this accounting. When a white dwarf radiates, the photon does not just brighten space, it subtracts from the remnant's internal energy. Across billions of years, the subtraction is visible as cooling. Across quadrillions, it becomes transformation. This is a kind of cosmic erosion, not by wind or water, but by radiation. The star is eroded by its own glow. A bright star fights gravity by creating energy. A white dwarf resists gravity by quantum pressure and loses energy. A black dwarf resists gravity in the same quantum way, but has little energy left to lose. That sequence is the argument of the whole life cycle. Fusion is temporary. Degeneracy can last. Heat leaks away. Matter remains. We can also see why black dwarfs belong to ordinary stars rather than extraordinary ones. Massive stars race through their fuel, build heavy elements, and die in supernovae. Their remnants become neutron stars or black holes, objects so extreme that they change space and matter around them. But most stars are small enough that their cores avoid that violence. They do not build iron cores. They stop at carbon and oxygen or, in some cases for more massive white dwarf progenitors, oxygen and neon. They leave compact degenerate remnants and enter the long cooling queue. That queue is enormous. The Milky Way already contains billions of white dwarfs. Some are young and hot. Some are ancient and faint. Many more will be made in the future as existing stars age. The population of future black dwarfs is not a rare footnote. It is the likely final state of a huge fraction of all stars that ever shine. If a future census of the dead universe were possible, black dwarfs could outnumber the dramatic remnants by far, and yet the first one has not arrived. That sentence remains the hook because it refuses to behave like ordinary astronomy. We are talking about one of the most common future objects in the universe, with a present-day population of 0. The most numerous future stellar corpse is currently absent. The majority ending has not begun. The best objection is that phrases like common future object sound too confident for something unobserved. But all future astronomy requires conditional reasoning. The sun becoming a white dwarf is also a prediction about the future, not an observed event in our own solar system. We trust it because it follows from stellar models tested on many other stars. Black dwarfs are similar in structure, though much farther removed in time. The confidence comes from continuity of physics, not direct observation. Where the confidence should weaken is where new physics might intervene. Proton decay, if real on relevant timescales, would undermine the long-term persistence of black dwarfs. Unknown interactions with dark matter or extremely rare gravitational disruptions could modify populations. Far future cosmology could change the background conditions. These caveats do not erase the expected cooling endpoint. They prevent us from overselling the ultimate fate beyond it. This is the disciplined version of wonder. It is not less cinematic than exaggeration. It is more cinematic because it lets the public stand at the boundary between known and unknown without being lied to. The black dwarf is not powerful because it gives us a dramatic certainty. It is powerful because it shows how much can be known and how carefully we must speak when time becomes too large for observation. In that sense, the black dwarf is a lesson in scientific language. Some words point to things. Some words point to processes. Some words point to endpoints of processes not yet reached. Black dwarf belongs to the third category. It is a name attached to the direction of cooling. It is a destination label on a road whose travelers have only just started. That road begins in light. It ends in darkness. But between those two lies a vast, structured, measurable decay. White dwarfs do not simply vanish from one category into another. They pass through temperatures, luminosities, colors, internal phase transitions, atmospheric changes, and gravitational rearrangements. The black dwarf is the end of a long physical biography, not a switch flipped from white to black. When people hear that a black dwarf emits no light, they may imagine a perfect black sphere. In reality, the boundary would be less theatrical. It would become undetectably faint long before any absolute final state. What counts as black depends partly on the background, the detector, the temperature, and the observational era. In the far future, with the cosmic microwave background far colder, the standard for darkness itself changes. A black dwarf is therefore a practical endpoint, not a magical threshold. This matters because it keeps us from treating labels as events. There is no single universal moment when a white dwarf announces that it has become a black dwarf. There is no flash, no sound, no border crossed with ceremony. There is gradual fading until the remnant is effectively dark. The category is useful because the physics is real, but nature does not care about our labels. That may be the quietest truth in the story. Nature makes continuities. Humans make names. White dwarf, black dwarf, degenerate era, dark era. These names help us think, but the universe only evolves. It radiates, expands, cools, collapses, crystallizes, tunnels, decays, or persists. The black dwarf is one of our names for a stage in that evolution. Still, names have power. Without the name, the idea would dissolve into a vague statement that white dwarfs cool. With the name, the future gains shape. We can imagine a universe filled with star corpses that no longer shine. We can understand that darkness will have structure. We can see that the end of starlight is not the end of matter. The black dwarf also changes how we think about heat. Heat feels temporary in daily life because everything around us exchanges it quickly. But in dense astrophysical objects, stored heat can become almost geological, then cosmological, then nearly eternal by human standards. A white dwarf is a battery with no charger, but the battery is so massive and so insulated that it takes longer to drain than entire civilizations can imagine. There is a strange mercy in that slowness. The universe does not rush into darkness. Even after fusion stops in a star, the afterglow remains. Even after the living star dies, its core shines. Even after billions of years, the oldest white dwarfs still carry warmth. Darkness is coming, but it is patient. The cosmos fades with an almost unbearable gentleness. That gentleness should not be mistaken for comfort. The far future is not hospitable. It is cold, sparse, and quiet. But the path to it is not abrupt. The black dwarf teaches that cosmic endings can be slow beyond comprehension. Not every apocalypse is an explosion. Some are the absence of any new heat, extended long enough to become destiny. If there is a final image to hold, it is not a single black dwarf alone in space, though that is haunting enough. It is the present sky above us, full of stars that have not yet become their remnants, full of white dwarfs, still too warm to go dark, full of photons crossing the universe before the long silence. The black dwarf is the future shadow cast backward onto that sky. It tells us the light is temporary, and therefore worth understanding while it lasts. The universe has not made a black dwarf yet. That is not because the physics failed. It is because the clock is young. The stars have died, but their corpses are still warm. The cooling has begun, but the deep future has not arrived. Somewhere in the equations, black dwarfs are waiting. Somewhere in the galaxy, white dwarfs are becoming them with a slowness that makes patience look like a fundamental force. And perhaps that is the best way to end, not with certainty pretending to be prophecy, but with a careful promise. Under the physics we know, the white dwarfs now cooling throughout the cosmos are moving toward black dwarfs. Under assumptions about stable matter, many will remain as dark, degenerate remnants for spans of time that make the current universe seem young beyond words. Under more speculative models, some may even find one final route to collapse or explosion. Each statement has its own confidence level. Each belongs in its own place. Science is strongest when it can hold those levels apart. It can say this is observed, this is inferred, this is expected, this is possible, and this is unknown. The black dwarf requires all five: observed, white dwarfs; inferred, their cooling histories; expected, their eventual darkness; possible, their far future transformations; unknown, the final laws governing matter across timescales no experiment can reach. The story is not smaller because of those distinctions. It is larger. It becomes a map of how knowledge works at the edge of time. A black dwarf is not just a stellar remnant. It is a boundary marker between astronomy as observation and astronomy as disciplined extrapolation. Tonight, black dwarfs do not exist. Tomorrow, they will not exist. 1 billion years from now, they likely still will not exist. But the universe is not done. The white dwarfs are cooling. The light is draining away. The future is being built in silence.